Hi, hello guys, welcome back to my YouTube channel Abhi in Kannada. Today we are going to discuss about thermionic work function of metals and also the Richardson Dushman formula, which is popularly known as Richardson equation. Now let us see. Before going to Richardson Dushman formula, we discuss few things briefly about this topic. These two persons are the Richardson, the Sir Owen Richardson and Sir Saul Dushman. Majorly, Sir Owen Richardson is theoretically derived the thermionic emission of metals in 1901. Then later, Sir Dushman is modified this equation, experimentally verified and determine a constant B, that is the Richardson constant in the Richardson Dushman formula. Now let us see the thermionic emission. What does this mean, thermionic emission? Let's see in the figure. We clearly understand in the figure what is thermionic emission in metals means. The emission of electrons from the metal surface when it is heated is called thermionic emission. These liberated free electrons are called thermions or thermoelectrons. The topic is simple. Thermionic emission means the emission of the metals from the metal surface when it get heated is called thermionic emission. Now what is thermionic work function? Let's see. It is also known as thermionic work function is also known as threshold energy. Or what is threshold energy? The minimum amount of energy which is required to remove the electrons from the metal surface. As simple as that, we discussed in the previous, the minimum amount of energy which is required to release these electrons from the metal surface is called thermionic work function. How it depends on the nature of the metal and metal surface temperature also. Work function which is measured in, we all know, electron volts. Then why we need this thermionic work function? Why it is important? It helps to understand how metal emit electrons when it heated, and also it is used in the applications like X-ray tubes, cathode ray tubes, etc. Now let's see some few examples here I mentioned. Tungsten, which is one of the best example for the thermionic work function. It has most suitable electron emitter. It has high melting point because it has high work function. When it is coated with the thoriated tungsten, when it is coated with the carbon and thorium, then it's called thoriated tungsten. It has low work function, which is 2.6 electron volts. Then when tungsten is coated with alkali metal oxides, then if the tungsten is coated with alkali metal oxides, like some examples of alkali metal oxides are barium oxide and strontium oxide or cesium oxide, etc. It has work function only 1 electron volts. These are some metals with their work function: sodium and lithium, which are 2.3 electron volts work function, zinc, calcium, cadmium, aluminium. These are some examples of metals. Now let's come to the Richardson Dushman equation, which is I is equal to B into T square into exponential of minus I divided by KT, where B is the Richardson constant, or which is constant for all the metals. I is the current density of, then T is the absolute temperature, then psi is the work function or thermionic work function. Then we all know K is the Boltzmann constant and T is the absolute temperature. Now let us see the experimental determination of the work function. So let us consider the Richardson Dushman equation. Let us I is equal to b to t square into exponential of minus I divided by kt. So taking log on both the sides, so it will become log I is equal to b in log bt log b plus log t square into log and exponential were cancelled, so remaining is minus I 5 divided by kt. So this is enough. Then we rearrange this equation. Log I is equal to log b plus log t square minus 5 divided by kbt. So log I, this can be rearranged. We get log I minus log I divided by t square is equal to log b minus 5 divided by kt. How we get log I divided by t square means, here we rearrange log I minus log t square. So log a minus b is equal to log a by b. So log I divided by t square, it will become log I divided by t square, which is equal to log b minus 5 divided by kt. This is the final expression of experimental determination of the work function. So let's see the application of Richardson-Dushman equation, where we use this formula in electron tube research and technologies and thermionic well, cathode ray tubes, etc. Some other fields also we use this formula. Thank you so much for watching. Please do subscribe.